you to ask the question on your behalf. We'll do our best to include as many questions as possible online. However, if your question couldn't be included, then we'll send it directly to the speaker and who would be able to respond to you directly. And finally, again, a request to all speakers, please keep your audio off for when you're not speaking. And if anybody gets cut off for any reason, then please rejoin the meeting. We're going to have a quick poll, and I think Luciano is going to announce the poll.
Okay, good morning, everyone. My name is Luciano Batista, and I'm kind of coordinating this event today with Allan. And before we start, we'd like to ask you to do a quick poll where we are going to collect some demographic information from you, from the audience. It's just for monitoring, the attendance, and we can see, for example, we can measure general interests from different groups, different backgrounds, etc. The information collected will be kept confidential, of course. You're not going to publish anything. It's just for our internal monitoring and reporting to the research councils. So Pamela is going to start this quick poll in a while, shortly, yes. And we're going to give you 3 minutes. It's a quick one, 3 minutes just to click some of the information, important information for monitoring. And then we will follow up. Thank you very much for your attendance today. And I hope you enjoyed the event as a general. Thank you. So Pamela is projecting the poll now. I think it's up and running. Yeah.
Yes, it is, Luciano, and the attendees will respond, and then we can resume. Thank you.
Brilliant, thank you.
Okay, 77% vote has been completed. Please be quick. Okay, 81% voted. Right, it's 10:10. We can start. Luciano, I'm going to end the poll now.
Okay, thank you very much, Pamela. And we still can see the poll in the screen, but thank you everyone for providing the initial information for this event. We're going to have a number of speakers today, and following the agenda here for the event, the first speaker is going to be Professor Allan Matthews. Professor Matthews is a fellow of the Royal Academy of Engineering, and he's also professor of surface engineering and tribology in the Department of Materials and director of the PSRC Network Plus of the DSM network that you are attending the event today. Professor Allan is based at the University of Manchester, yeah, so Department of Materials at the University of Manchester. And he was a pioneer in the field of surface engineering in the early 80s. He instigated the first surface engineering laboratory, which became the Research Center in Surface Engineering. And he's also was the founder of this laboratory. He has published around 400 academic papers and several books and chapters. He has leadership roles in many professorial and learned societies, including Executive Committee of the Advanced Surface Engineering Division of the American Vacuum Society. And between 2014 and 2019, he sat on the PSRC Strategic Advisory Network. On the Knowledge Transfer Network Specialist Interest Group in Surface Engineering and Advanced Coatings, he represented academic standing and helped guide industrial research strategy in the coating sector. He has received a number of awards, including the IOM3 Gold Medal in 2011 and the AVS RF Banshall Award in 2018. And he also received in 2020 the Leading Scientist Award from the European Society of Thin Films. And he's also editor-in-chief of the Elsevier journal, Surface and Coatings Technology. So it's quite an extensive list here. So thank you, Allan, and I'll pass it over to you for your presentation.
Thank you very much, Luciano. Can everybody see my screen, my presentation there?
Yeah, Allan, I can see it perfectly.
Okay,
yes.
Thanks very much, Adrian. Okay, so I'm going to give you an introduction to the EPSCC Network Plus in Digitalised Surface Manufacturing. This is a collaboration involving Manchester University, Queen's University Belfast, and as you've seen, Adrian Murphy from Queen's is going to be speaking during this webinar. Also involving the University of Sheffield, London South Bank University, and Cranfield University as well. So now my slides are not moving forward for some reason. Very strange. I think I'm going to have to do it this way. I'm sorry about this. For some reason, the slides aren't moving forward. Can you see this? Can you see the slides?
Yeah, yes, we can, Allan.
Yes, please.
So you can just see the smaller version of the slides.
Yes, yeah.
For some reason, the large slide presentation isn't incrementing through. So I'll do it this way. Okay, so what do we mean by digitalized surface manufacturing? Well, put simply, it means being able to represent in a digital form coatings and the processes which are produced. And digitalization has been found to be particularly vital for the surface manufacturing sector. All this was very much triggered by a report from the Knowledge Transfer Network, which was produced in 2014. I don't know if you're aware, but the KTN, if they see a sector which they think requires special attention, they will set up a special interest group. And they did such a thing for the surface engineering and advanced coatings sector. That was made up almost entirely of industrialists. And they produced this report, Time for Strategic Change, UK Surface Engineering and Advanced Coatings Industry. And that led to a number of recommendations. They also did a study into the size of the market. In the UK, the coatings market is worth about £11 billion. And that 11, and you can see here on the right, or that it impacts on all the main industrial sectors. So oil and gas, automotive, construction, aerospace, excuse me. And the coatings, those £11 billion worth of coatings are actually used on over £140 billion worth of products. And those £140 billion worth of products are critical within companies with a total turnover of 383 billion. So you can see that coating is extremely important, and because this study, this special interest group study, found that it was lagging behind other sectors of industry, there was a certain need to support it more. So at the same time, the government brought out its industrial strategy, which identified 4 main pillars of support: AI and data, mobility, aging, and clean growth, which goes on to affect all of the main productivity influencing aspects of industry. Furthermore, the government's Made Smarter review said that the UK could benefit to around about 455 billion over the next decade if it introduced industrial digital technologies. So you can see everything was moving towards supporting industry with digitization and supporting the coating sector, but it was found that no UK university had all the required interdisciplinary expertise, and there was a lack of connected knowledge. So this is, again, reiterating that the UK is lagging behind other companies, other nations in terms of digitalization, in terms of productivity, and that was particularly acute amongst SMEs, and many of the coating companies are SMEs. So this is all part of the move towards Industry 4.0. So you all know that we've gone through Industry 1, which was mechanization and industrial revolution, and then came mass production with Henry Ford, etc. Industry 2, then we had Industry 3, PC and automation, and now we're into the smart factory, Industry 4, and that involves the manufacturing being monitored using cyber physical systems which monitor and control the manufacturing process. So we're part of that digitalization move, and in our particular network tries to help this with the coating sector. Now, again, during the special interest group study, we had, as I mentioned, many industrialists, and this was a particular slide that came from Rolls-Royce. It looks complicated, but it's not. What we actually found that presently the coating sector focuses on end user resources and supports current products rather than bringing in coatings at the design stage. So what we need to do is introduce coatings into the design for manufacture aspect of manufacturing. So, and that further involves having standards for coatings, validating those standards, and having process control in a full Industry 4 manner, and also feeding back service experience. So you can bring through coated products to have the best performance by actually designing in the coating during the design stage. So our aim as the Digitalised Surface Manufacturing Network is to try to link academia and industry. So what we do is we run feasibility studies, we have special ECR, early career research and development, and inclusive learning and webinars. We have workshops, we do horizon scanning, we have special training and development in academia, and we support research which will help to bring through digitalisation. And pull, in a way, we're covering what they call the valley of death, the link between academia and industry. And we also take full account of societal challenges, including sustainable development goals, climate change, green manufacturing, healthcare, and biosafety. So that's what DSM aims to do. And we are helped in this by an industry body called SELF, the Surface Engineering Leadership Forum, which we're very fortunate that at the same time that the academic group was set up, industry set up SELF, which and we work closely with them. The founding partners for our network are shown here, and we started off with 27 members and 16 organizations, and now we have about 400 members and about 64 organizations, growing all the time. And what we're trying to do, this is a slide from a colleague of ours called Brian Alcock, who is an industrialist with a company called TRL9. We're trying to introduce what they call the transformational change in the sector. So we're trying to move from what they call the 7 waste methodology to plugging the digital gap to applying design for manufacture. So we're trying to move the industry with the support of academia to move from being match fit to being best in class to being world class. Okay, and to introduce a transformational change in the industry. Now, I mentioned the 7 wastes there. Many of you will be aware of this. If you do a Google search and you put 7 wastes or 8 wastes in, you will get this kind of slide. And what it tells you is that with digitalization, you improve productivity because you reduce overproduction, you reduce inventory, you reduce transportation, reduce motion, reduce wasting, reduce defects, and reduce overprocessing. It's in order to increase the slice of this pie that is value added. So that is what our aim is, to introduce digitalization to facilitate these improvements. And by closing that digital gap that exists in industry at the moment, we can give them better utilization of assets, a reduced dependency on tacit knowledge. We can reduce the time and the cost linked to product verification. We can improve and give visibility to all business performance metrics, manufacturing metrics like yield, right first time, cost, delivery, quality, and equipment effectiveness. We can enable and improve design for manufacture, open up new business opportunities, and provide a framework for developing a more resilient business. Now, one thing I want to say to you, and I want to take advantage of this opportunity, is to say that not only do we improve the sustainability of the manufacturing, but we improve sustainability as a general topic. And the reason I say that is that coatings directly impinge on sustainability. So, for example, coatings allow scarce materials resources to be conserved by applying the scarce material at the surface where it's needed rather than making the bulk from it. We reduce energy usage in transport. For example, we reduce friction in using coatings. We reduce fuel consumption in aircraft using thermal barrier coatings, and coatings also assist in lightweighting activities. So we also improve the efficiency of power generation, such as ground-based turbines and wind turbines. And many of these coating processes can have reduced toxic effluents. So we're addressing not only the manufacturing sustainability, but the broader sustainability agenda by making the manufacture of sustainable coatings more effective through digitalization. So, for example, coatings help in energy sustainability through generation and conversion, through conservation and energy storage. So we have coatings that help in energy generation and conversion on turbine blades and reducing corrosion in offshore and onshore. Even coatings are even used in producing photovoltaic devices and in fuel cells. So very important that we can make these things more effectively by using digitalization. In terms of energy conservation, as I mentioned, we can reduce friction. There are solar control coatings on architectural glass, polymer coatings to control building temperature, etc. All of these we need to produce digitally, and we're using digital technologies to make them more effective. And then finally, the coatings and energy storage, of course. Lithium-ion batteries are basically multi-layer coatings, and hydrogen fuel cell coatings, such as yttrium-stable zirconia, are also clearly very important in that kind of energy storage system. Now, previously, of course, everybody was worried about oil running out. All the big talk was about oil running out, and we need to make engines more efficient. Of course, the oil's not going to run out now because we're going to stop using it. But instead of this has come the global warming risk. So everything we've done to try to reduce oil usage and to make things more efficient are still valid for this kind of sustainability requirement. So lots of work was done on engines and reducing the efficiency. And you think, well, do we need this? Well, we still benefit from this for reducing friction in engines, because some of the parts in the engine are things like gears. And we can have gears which run more efficiently using our coatings. And of course, those gears are used in electric vehicles in the same way as they're used in internal combustion engine vehicles. So it's a lot of that research that was done on the internal combustion engine is still highly valid for, and you can see here that we can extend the fatigue life of gears using particular coatings. So coatings extend all kinds of gears, reduce pitting, reduce seizure, and extend fracture limits. So these gears are used in, for example, in wind power. And it doesn't matter if it's a directly driven wind power turbine or a gearbox operated one, which still needs coatings in it, or benefits from coatings, and we need to be able to produce those coatings more effectively. Now, one of our collaborators I mentioned already, Brian Alcock, has done a lot of work in introducing the cyber physical devices into coatings manufacture. So this is a robotized thermal spray system, which is in Brian's factory, which includes cyber physical monitoring of the thermal signals, the visual signals, and the acoustic signals. So you can monitor noise peaks, and this is all part of the smart factory concept. We've done this type of approach in a technique called plasma-assisted electrolysis, which can be used as an in-liquid plasma, which can be used for plasma polishing, for treatments, and for coatings. And that particular technique is extremely useful as an alternative to anodizing. So compared to anodizing, it has no toxic reagents. It doesn't use, say, for example, sulfuric acid, which conventional anodizing does use. So this particular technique is ripe for utilization in a sustainable manufacturing scenario. That particular technique includes a thing called an electrolyzer, power supply, digitalizer, and computer, and we can monitor it. And what we can do is we can develop a process model, a geometrical model, and we can link it the process back through cyber-physical monitoring to produce a digital twin of the process, which is represented by the black line there. So we have a digital twin of the process, and we can then compare our real process against that digital twin line through a cyber-physical interface in order to have a full understanding of the process as it proceeds. And of course, you all know that it's better to build good quality in than test bad quality out. And this is means that with this process, rather than completing and then inspecting and then rejecting, or even part building and testing and rejecting, we can go straight to a continuous digital twin monitoring and in microseconds rather than hours or days to benefit fully from digitalization in that particular coating production. Another example of a sustainable coating is this, it's called a pintle bearing of an undercarriage. Previously, this pintle bearing was made of steel and bronze, and by replacing this with an advanced coating, diffusion treatment of titanium, followed by a coating, we were able to halve the weight. So we were able to take hundreds of kilograms out of the weight of the undercarriage. And it's quite unbelievable. You can get a fuel saving of about 7.6 million pounds per plane over the life of each aircraft, just by a few hundred kilograms weight saving, which was representing about 36,000 tons of CO2. So the message here is digitalization. Not only does it make manufacturing more effective and efficient, but it also considerably enhances the broader sustainability agenda. And we're doing that within the
Allan, sorry,
a strong web presence, and we're on Twitter, LinkedIn, and we have a YouTube channel. So,
Allan, sorry, we are running out of the time. Thank you so much, Luciano.
Okay.
There is one question from Marlon to Allan. How do you envisage the role of coatings and digitalization in reaching a circular economy general awareness and implementation as part of a sustainable and holistic approach?
Well, I've tried to explain there that digitalization, not only does it make manufacturing more sustainable, but it helps in the production of sustainable products and products which aid sustainability, and particularly in the coating sector, which you know has lots of electroplating shops which may discharge effluents into rivers, etc. We're looking at techniques which remove that. But in the broader sustainability agenda, we help. That requires a transfer of information between the different people, the producers, the end users, etc., to educate them in the use of sustainable methods in manufacturing. I may not have completely answered that, so I'll look at your question more deeply and get back to you outside the meeting. Okay?
No.
So are we moving on to the next one now, Pamela?
Yes, please. Luciano will share his screen, and if you can introduce.
Okay. So I'll just give a short introduction to Luciano. So Luciano is a senior lecturer in operations management in the Operations and Information Management Department at Aston Business School at Aston University. He's actually an alumnus of the University of Manchester, and after graduating in computer science, he worked in the Brazilian ICT industry for 11 years before moving into academia. At Aston Business School, Luciano teaches operations strategy, international operations and research methods. And his research focuses mainly on sustainability aspects of operations, logistics, and supply chains. In particular, emphasis is on exploring the interface between the circular economy and the digital economy. And he's a chartered member of the Institute of Logistics and Transport in the UK. He's a member of the European Operations Management Association. He's a fellow of the Higher Education Academy in the UK, an editorial board member of the International Journal of Supply Chain and Operations Resilience, and is an editorial board member of Revista de Administração of the University of Sao Paulo. So I'd like to pass it over to you, Luciano.
Thank you very much, Allan. I hope you can hear me okay, everyone, and you can see my slides on your screen. How is it going over there? Can you hear me okay? Yeah. And see my slides? Yeah.
See the slides, yeah.
Okay, so brilliant. And I'm going to just give you an overview about the UK Manufacturing Symbiosis Network Plus, which acronym is UKMSN Plus, yeah. And this is one of the other Network Plus funded by the EPSRC. We are under the circular economy topic priority area for the EPSRC, which in a high level, it's part of the Manufacturing the Future portfolio initiative from EPSRC. So this Network Plus focuses on circular economy. And our take on that is developing industrial symbiosis capabilities in the manufacturing sector. Just to give you an overview about the partners in this network, we are working together with University of Exeter, led by Professor Roger Mole, and also we work together with Cambridge University, the Institute for Manufacturing, represented by Mukesh Kumar, and we got Andreas Isman from the Open University. She's an expert on computing and communications and adaptive software applications, and the Imperial College of London working with Theoni in looking at the part of material sciences and engineering, plastics, and etc. We conceptualize a vision for this network initiative, and our vision is to strongly position manufacturing research into the mainstream of scientific developments and impact for the circular economy. When you talk about sustainability in a manufacturing context, we can see there are lots of good initiatives out there in different sectors. So just to mention a few examples here, some very good initiatives in the food sector, chemicals, automotive and vehicles, clothing, textiles, and you name it. Just to give you an overview. In the middle, you get the packaging manufacturing sector as well, which permeates across different sectors. There are some very good initiatives, but they are mainly being developed in a fragmented way, in a kind of isolated way, sometimes in silos. And there is potential if you can, for example, create synergies across sectors. So you want to maximize collaborations across sectors. Let's not only amalgamate the good initiatives within sectors, but cross-fertilize knowledge and good practice across sectors. But to do that, we need a kind of approach. And the approach we decided to explore for enabling that kind of cross-sectoral collaboration was the industrial symbiosis approach, and to facilitate those kind of cross-sector collaborations. Why industrial symbiosis? Well, the circular economy has several schools of thought, as you can see here in these slides. Yeah, in cradle to cradle, the performance economy, the biomimicry, natural capitalism, blue economy, and regenerative design. And one of the pillars here, the main pillars, is industrial ecology. And within industrial ecology, industrial symbiosis is one of the main research streams within industrial ecology. It provides a kind of systemic approach to develop industrial collaborations, industrial synergies, looking at mutually beneficial relationships across industries. It lends from the systems theory and systems thinking perspective. It's all about developing resource efficiency, looking at life cycle extension. It can be planned and can be designed. You can design those collaborations. And it is strategic. You can look at it from a strategic perspective and a strategic angle. So it allows, by applying some of the many industrial symbiosis methods, frameworks, and practices, we can develop kind of organic growth of manufacturing collaborations and synergies across diverse sectors. That's what's most important for it. So by getting industrial symbiosis in the mainstream of developing manufacturing synergies and capabilities, we are kind of contributing to their positioning in the circular economy, maximizing resource exchanges and sustainability overall. So that's the idea. We developed a number of mechanisms to develop knowledge, to create knowledge. Yeah, it's called knowledge generation and transference mechanisms. So we developed kind of a series of sectoral specific studies where the main point, the main objective here was to look across the best practices in different sectors. So it's taking a look within sectors, so kind of horizon scanning, initial take. And from there, we look at how can we bridge, how can we cross-fertilize knowledge across diverse sectors. We call it these feasibility studies with a focus on linking different and diverse sectors. How do we link it? By applying industrial symbiosis principles, practices, and frameworks and strategies, and etc. It's a vast field of knowledge in itself, and it applies, it fits perfectly the circular economy context in terms of enabling resource exchange, as I mentioned. And all of this is continuously being disseminated and trying to generate impact in the industry. Yeah, we do have a well-defined disciplinary scope. So it's a multidisciplinary approach, as you can see in this slide. Yeah, we are looking at, for example, digital systems innovations, as Allan mentioned about digitalization is critical. It's all about dematerializing a number of initiatives and flows out there. We're looking at Internet of Things, artificial intelligence, and the application of other cutting-edge digital platforms like blockchain as well. The creation of information hubs to facilitate communication across diverse sectors, modeling and simulation, all these digital systems innovations that can enable and facilitate industrial collaborations. We will be also looking at materials innovations, develop novel materials with superior adaptability, superior degradable capacity, the safety of materials reutilization, and novel materials for additive manufacturing, for example. But all these technological innovations, they have to be translated into business practice. And then that's why I look at business model innovations, which are the ways to translate these technological innovations into production and consumption systems based on circular economy approaches. And we will developing symbiotic restorative manufacturing ecosystems, design of circular supply chains, distributed manufacturing networks, and restorative ecosystems, looking at logistic systems to implement and facilitate the exchange of resources, and enabling policy and the policies, policy making, and governance structures that facilitate and coordinate and validate cross-sector collaborations. So that's the idea. All these is about developing manufacturing symbiosis capabilities that are going to enable the shift, the manufacturing shift to the circular economy. So how we organize those exploratory studies in two different streams, as you can see here. The first stream was the initial take. We funded five different studies here initially, in 20K funding for each of the studies. We got studies from different universities here, looking at apparel and textiles, construction, food, aerospace, and packaging. And in the second moment, after these initial studies here, we moved into the sectoral bridging studies, looking at how to cross-fertilize knowledge and how to bridge different and diverse industrial sectors by doing restorative manufacturing ecosystems involving more than one manufacturing sector, looking at the digital technologies and systems and platforms to link different sectors, and also the flow of materials, the flexibility of materials to flow across different sectors as well. So there are more money here, more time, as you can see, 8K to fund new business models, and 100K for 130K to fund technological developments in digital technologies and materials technologies. Okay, and
Luciano,
just to identify.
Sorry, Luciano. We
Yeah.
need to hurry. If we can, wrap it up.
Yeah.
quickly,
Okay.
please. Thank you.
Okay, we will share these slides with you. We are aware of time, and those are the 5 studies from the initial take and the 4 studies recently selected for the cross-sectoral bridging exploratory studies. Thank you very much, everyone. And let's move on now to the next speaker. I'll stop sharing my screen here. And let me see, the next speaker here is going to be, according to the
Luciano, I think it's me. It's Andy Whyle.
Oh, Andy. Okay, so thank you, Andy. I was looking for the agenda. I could not find it. So, well, it's a pleasure. It's a pleasure to introduce the next speaker. It's Andy Whyle. Andy is member of the advisory board for the UKMSN Plus, and he's a sustainability specialist who has over 30 years of experience in sustainable manufacturing. And his expertise covers sustainability leadership, circular economy, natural capital development, networking, and collaboration. He's a fellow of the Institute of Environmental Management and Assessment, and where he chairs the Circular Economy Networking Steering and Corporate Sustainability Working Group over there. Andy is recognized as a Sustainability West Midlands Green Leader, and he's a proven leadership practitioner on a local, national, international basis. As a subject matter expert on the circular economy, he co-authored the Business Lens Evidence Chapter of the Government Office of Science, From Waste to Resource Productivity Report, which was utilized to create the resources and waste strategy for the government. And Andy has utilized his experience for DEFRA as well, working for advisor group for DEFRA and the UK Resources Council, representing the manufacturing sector's material users and producers to increase the circularity in the UK. He's a guest lecturer at several universities. His experience as a practitioner has led to several best practice case studies, developing and demonstrating circular economy solutions. Thank you very much, Andy, for making your time today to speak to us, and I'll pass it over to you.
Thank you, Luciano. It's actually it's a brilliant privilege to be able to speak today, so thank you. Let me know if there's any issues with the voice or the presentation, but we'll quickly move on before Paul Miller cuts me off. We're going to talk about a circular economy overview. If anybody wants to know me or wants to join me on LinkedIn, that's fine. There's the advertising. Let's get out of the way. Luciano's covered that. What we're going to talk about. Why should you be interested in circular economy, first of all? And then what is it and how to demystify it, which is a critical thing, I think. And then we look at a few examples, which would be good. So let's have a look. Things change. Products change. Look at that, over 25 years difference for a laptop. And that was what, I was talking to my father yesterday about a mobile phone that he had that looked like that. People change. People now care more. Yeah. And it's mainly due to this chap here, to be fair. What's the problem then? Why should you be interested? So the biggest problem, I think, is world population rise, as explained by Sir David, which will put demands on everything, to be fair. That's generally known, but what's also not known and generally understood is that will be a demographic change in the fact that the developing world will demand more, become the developed world, and people want, lifestyles will change. There'll be even more demand on resources. Many people, and I've met these two gurus of sustainability years ago, have talked for a long time now about how the world is going to change, and we're now seeing that change. So what's the problem specifically with technology and rare materials? So over modern history, resource conflict has been mainly over fossil fuels, oil wars and things like that, something you may remember. Now it's access to rare earth materials, which is vital for future technologies, and resources such as cobalt and lithium are potential material conflicts of the future. The new technologies we crave for, required to decarbonize our economy, depend on these raw materials that are both critical and scarce. Anybody who knows the elements songs can sing along with that. Platinum, palladium, niobium, neodymium, gallium, and germanium, wherever. These elements are essential for fuel cells, photovoltaics, and LEDs. And the manufacturing industries of the future depend on these materials. So what's the challenge? And this is not a slight at the Chinese approach, who've been very savvy in their business ways, but Chinese dominance of the global graphite supply, which is 64% production and 24% of reserves, threatens the ambitions of our planned gigafactories. So Andy Street was talking the other day about West Midlands gigafactory. That's all brilliant. I hope we have one here. And Mark Thompson, who's going to speak today, would have explained how we're working on remanufacturing batteries from this process. Sometimes you've got to realize that's really essential, otherwise you're not going to have the supply chain. Few nations hold sufficient of the resources. They are fundamental to the economic growth in the UK, and even for the EU to achieve its target of electrification by 2030 would deplete the known world reserves of lithium within 5 years and cobalt within 12 months. And there is a graphic I've stolen from The Guardian, which shows that over the next, by 2040, it will increase by 4 times the demand on those materials. Another classic example is gold. Rare earth elements are limited and difficult to mine. So gold mining efficiency, it takes 1 ton of gold ore makes 1 gram. Gold is another element, estimated to run out in 20 years. Numerous wars fought over gold, obviously. Today, though, there's more phones than people on the planet with an average lifespan of 2 years. If it's not sent for waste electronic recycling, it's then incinerated or landfill, or often hidden in people's drawers. But it only takes 40 smartphones to get the equivalent of 1 ton. I looked at the risks and impacts. I was in an event talking about climate adaptation the other day as a facilitator. Yeah, we've just discussed things like this. So stuff, consumer electronics. What happens if there's no stuff? There'd be unemployment. Nobody's going to make things. Poverty, crime, obesity, demographic equality, social unrest, and from that, increased death rates. So yeah, a bit of an impact. So let's talk about what is circular economy. I pinched this from my colleague Debbie Ward, who chairs the Circular Economy Club in Birmingham. This is one of the most up-to-date and simplest ones, but a circular economy is restorative and regenerative by design and aims to keep products, components and materials looping at their highest utility and value at all times. Under those 4 things, so you design out waste and pollution, keep products, materials in use, generate natural systems, and powered by renewable energy if possible. You can have models, net zero contributors, and designing out waste aspects there. This is probably the most up-to-date one I've seen, but going back in time, this is one from IEMA, from Waste and Resources Report. And again, it talks about take, make, and use and discard and dispose, and builds in a circular economy aspect, which is a bit strange because it's box shaped, but never mind, you get the point. This world famous Ellen MacArthur butterfly diagram, which talks about biological and technical nutrients, even built in hunting and fishing. Bless it. Okay, that's good. I could spend time on understanding that, but it's a bit difficult to convey. Where I worked for Rico for 30 years, back in 1994, they came up with the Comet Circle, and it talks about the user represented by a sun and orbits of materiality. A bit difficult to grasp. So the mission is to get people like box dwellers, if I used to be one, to understand this. So what's a box dweller? Box dweller wakes up in the morning in a box-shaped bed, in their box-shaped house. They need money, so they rush off to work in their box-shaped cars, go to work in their box-shaped factories, emit some pollution of some form or another. They put stuff in boxes and it goes off to customers. And at the end of the day, they clock out, drive in their box-shaped cars and go back home. After a while, you get to realize that things are more circular. The world is circular, and you should be taking a different path, shall we say. And that's what we're doing at Sustainability West Midlands with a map that looks at resource efficiency. So to address this problem of understanding what the circular economy is, I was a few years back trapped in a room with a number of professors and the chief scientific advisors who, as we all know, professors, nobody likes their own voice. Sound of their own voice like a professor, obviously Allan and Adrian excluded. Yeah, I couldn't get a word in edgeways, so I went back and started to bullet point what I do as a manufacturing operation. And over time, working with a number of universities and the IEMA Circular Economy Network, we sort of fleshed that out into a process flow diagram approach that people could follow. Each part of the process, it just gives you an overview of what you need to look at, but then drills down underneath to examples of that and what you need to consider and some tools that you could use. It looks at design, supplier engagement, resource selection, your sustainable business, how you interact with your customers to get the products back, what you do with them when you get it back, and then review it in a whole new model intro cycle. And we ask simplistic questions such as, so we can get more people to understand it, such as, is it actually needed? Can it be used again, which is remanufacture and reuse? Do you actually need so much of it, which is reduction? If you can't use it, can someone else, which is a small world for industrial symbiosis? Or can it be turned back into what it was or something else recycled? Lots of companies look at this now. There's examples all over the place. Michelin tires, been doing it actually since about the 1920s, where they retread tires on a contract basis. Netflix look at non-physical products. 75 million subscribers, completely different business model, but it produces all the things about DVDs or players and things like that, which is for longevity as well, engineered for ultimate durability. That umbrella, if it fails, they will replace it for free. And there's even things like Tilly hats as well that do that now. Skip to the bottom one, which is Colour Reel, which I like. One of these ones is one of the last things we're developing at Rico, where instead of multicolored threads, it was replaced with a single white thread that you print ink onto, right? Which means that you don't have so many product changeovers and you don't throw all that waste away. There's even things like laptops now, remanufactured laptops where they also plant trees to offset it. But one of my ultimate favorites recently I've come across is this Jinan Xiaobin Eco Farm as a circular food solution, where they take 200 tons of food waste a day. They feed it to 1 million cockroaches. And what for? The cockroach waste is used as fertilizer. But when the cockroaches die, which they do eventually, they're fed to the chickens, and bizarrely, chickens get fed back to the restaurant. So truly circular economy in the food sector. Really brilliant. So to summarize, the strategy is to develop sustainable manufacturing to maintain materials for productivity. Bear that in mind. It's recognizing resource risks, improving the skills involved with that, such as circular economy networks and workshops, innovating alternative process materials, Importantly now, digitization of resources and processes to maximize the material values. The Internet of Things that Allan mentioned earlier, really important in capturing those waste streams. It's also about increasing the entire value chain, awareness of the circular models, getting everybody involved, circular economy deployment, and diversification of what we do in operations to become more sustainable. With the result that manufacturers and customers are now beginning to grasp resource conservation and the circular economy as a strategic issue. With reduced environmental impact of operation, extending the life cycle of materials, resulting in an increased ability to maintain future business continuity. And for me, that's exactly what it's all about. To become an effective business continuity, you need to become more sustainable. Thank you, Luciano.
Thank you very much, Andy, for a brilliant presentation. Very interesting case and examples. And we have to move on now for the next speaker. It's going to be Professor Adrian Murphy from the Queen's
Sorry,
University.
Luciano. Sorry, Luciano. There is a question for Andy.
Oh, okay. Brilliant. Sorry, Pamela. Thank you for spotting that out.
Just a question from Kieran Leyland. What were the 5 R's of a circular economy?
Oh, good point. I didn't want to put that in. I was trying to keep it short. Refuse, return, reduce, reuse, recycle. Right. So in terms of the Kaizen continuous improvement aspects that we taught in the manufacturing environment, it was a case of keeping that simple. Refuse and return replied to the purchasing department, the engineers to sort that out. Reduce, reuse, recycle actually came into the operations where anybody in the operation would go, well, why do we need that? Could we reuse that in the organization, or could we segregate that to be made, send off as a recycler and generate revenue, hopefully.
Mm-hmm. That's great. Thank you. I'm aware of time, so perhaps we can, for example, address the questions later. I think we have to move on with the presentations. Thank you very much again, Andy, for your presentation. The next speaker is going to be Professor Adrian Murphy from the Queen's University of Belfast. And let me get here. I'll pass it to Allan to introduce.
I'll just say a few words about Adrian. Adrian is a Professor of Aeronautical Engineering at Queen's University, Belfast. His research focuses on predictive modelling, in particular developing methods to understand the influence of processes on product in-service performance and cost. Adrian is a fellow of the IMechE, and he sits on the Royal Aeronautical Society Structures and Materials Specialist Committee, ESDU Aerospace Structures Committee, and the IMechE Aerospace Materials and Structures Technical Activity Committee. Adrian is the Deputy Director of the Centre for Intelligent and Autonomous Manufacturing Systems, IMS, an interdisciplinary centre spanning the disciplines of engineering, computer science, mathematics, statistics, and psychology. Adrian has published over 160 journal and conference articles, which are listed on his web pages. And Adrian is a winner of the Thomas Hawksley Medal 2006, the Kenneth Harris James Prize of 2006, and a Sage Best Paper Award in 2012 in the Journal of Materials Design and Applications. And I should say that Adrian is also a co-director of our Network Plus. So over to you, Adrian.
Thanks very much, Allan. Can you hear me and see my slides?
Yeah.
Thanks very much. So I really have enjoyed the presentation so far, and I'm going to try and keep to time. So I want to introduce a little bit about simulation and digital manufacturing technology. And in particular, let me see if I do that. I want to Get my screen right. Have my slides progressed there? I think they have. I want to introduce those technologies, and I appreciate some people in the audience will be familiar with them, but I want to present them so I can give you some examples of what we're able to achieve today, and then what I hope the challenges, or I see the challenges and the opportunities in the future to use technology in the aerospace and beyond design domain to make sustainable products and towards, you know, a circular economy. So I'm going to introduce the kind of digital manufacturing simulations. I'm going to give you some examples of work we've done in those spaces. The first one looks at a number of basically manufacturing technologies and builds tools to study those. The second looks at a supply chain and tools to study a supply chain. And then from those, I'm going to hopefully produce some interesting, or at least points to talk about challenges and opportunities. So in terms of digital manufacturing, if we think about how we design a product, we use CAD, we create a virtual representation of a product before we start physically making it. And digital manufacturing is really the sister tools we use to create the virtual manufacturing environment before we start building factories, before we start buying equipment. And the idea is that we can virtually demonstrate and verify that we have the right processes to make the product. And ideally, we can do that concurrently. So as we design the product, we can design the processes, and we can have the two mature together. And we've lots of tools to do that look at, you know, individual bits of processes to complete supply chains, to look at how humans operate in those spaces, how robots operate in those spaces, etc. And the outcome of those digital tools is the systems of manufacture, is the work instructions for operators, the code for robots to put things together. It's the footprint around tooling in the factory. It's the combinations of manufacturing stations that make up a factory, and it's a global supply chain. So it functions at many, many different levels. And what we want to get out of it is a complete system. And actually, what's quite interesting is that we get quite a lot in creating those digital tools and using those digital tools about the kind of what companies do very well and what makes them profitable, which is how they manufacture and how they achieve things on the shop floor. So there's lots of organizational learning and knowledge within those processes. Within that whole suite of digital tools, there's simulations, and simulations again can be, you know, at the very highest level, applying system dynamics to complete global supply chains. It can be looking at individual factories and using things like discrete event simulation to understand how products flow through the factory. And it can be down at individual processes where you're putting in a rivet and you're introducing stresses to the component and you're introducing distortions. And we use those simulations as engineers to get numerical answers, so we can say the number for this is bigger or lower than another process, and we can make decisions and select processes and routes and etc. to put things together. And there becomes a connection here between, you know, what we want to achieve on the shop floor and how the product performs in service. Because if we do something in a certain way, we'll introduce residual stresses, etc. And, you know, that affects how long or how the performance or the product functions in service. So hopefully that gives you an idea that these digital tools that we use to make manufacturing systems go along with the tools and systems we use to make products or design products. So I want to give you an example or two examples of this. The first one's part of a European project where we worked with Saab and we worked with TWI on the project, and we were trying to develop welding technology, but also beside that, a set of digital tools to allow Saab to make decisions about what was the best way to make aircraft cargo bay doors. Should they use advanced welding technologies, be that, you know, laser welding, which is what you see in the video, or friction stir spot welding, or manual riveting, or automated robot driven riveting processes. So we we worked with them to understand the processes. We built various digital models of various different processes at different levels, you know, down at actually where the weld was occurring. And then as you see on screen at a cell level where we've a number of processes coming together to make the cargo bay doors. And we did that to generate a base set of data for the different processes, so that we could start to construct a toolkit for the engineers to perform trade studies, to work out what was the best technology for particular applications, in this case, particular aircraft. And the most interesting thing about this is the way we tried to do it was we tried to do it such that it was future ready, so that if you make these choices and you design the process to go with the product, and then you start producing it, and you start to make a factory, you start to produce parts, you start to produce data, because you've a digitized process, which, as Allan mentioned, is the opportunities are endless when we start to do this. You get a continuous flow of data. So the tools you used for design can be the tools you use to improve your process through the life of the product. And for that, we tried to create this architecture, which is shown in the left there, where we've a store, which is where the data is. And then we have a series of process models where we can basically ask the questions. And then we've a set of tools to help visualize the results. And these are, you know, in the main open source, they're common tools, but it works in a way where the data is flexible. We can swap in, you know, simulated data for real data, and we can play tunes and look at trying to optimize the product or the process throughout its life. So if we expand that up, you know, we were using SQL for the data source, we were using Python for actually running the scripts, etc., and then Power BI to interrogate. So pretty common kind of generic tools. So I'll kind of dig down into these a little bit, but if you see there's another example of a simulation video playing there, you know, that we're using discrete event simulation, which allowed us to say, you know, how long a process would take, which told us if we have to make so many a year, how many robots we needed, what footprint we needed, how many jigs and tools we needed. When we looked or selected a robot, we could work out what kind of robot, the path that the robot would take. We could work out then the influence of the production process on the performance, because we'd understand things like how the heat dissipated as we perform welding processes. We can look at residual stresses and stuff. And that data set then could be manipulated or brought into the analysis process, the process bit, where we could run the calculations. And for today's audience, when we're thinking about sustainability and we're thinking about circular economy, you know, when we set out to do this project, many other projects like this, we set out to look at the cost. But as we did that and we talked to the company, we kind of said we can do other things. We can give you an impact of, you know, where you use your energy and the footprint and stuff. And, you know, that became very interesting to the company. So although these process models are primarily built to generate cost information, we can manipulate them and use them to calculate other things. And in particular, if we think about the circular economy and we think about that process of generating data, you know, virtual data to select the process, and then we start to use real data to refine the process. If we start to think about a circular economy where we start to have products coming back in through our factories, you know, we're starting to build the infrastructure to say, well, actually, this has had a 20-year life. So it's not going to behave the same next time it's welded. It's not going to behave the same maybe as we take it apart. It's going to have distortions. It's going to have already a fatigue life. It's going to have crept. You know, when digital models, simulations that capture the physics can uncover some of those. And there's the potential, the architecture here to start designing for a circular economy and reuse of products. And then a massive piece of this is communication. You can get all this data, you can process this data, you can predict what might happen, but what you really need to do is give it to the engineers so they can understand it, and really also put it in a way that they can explain to the accountants that it makes sense, that the investment is in the right areas, they're making the right choices. So there's lots of tools to visualize and to look at data. And with this particular example, you know, we were looking at different manufacturing technologies. So I felt I needed to show you a slide where, you know, 4 different technologies. You can see the time to produce parts change, but actually the capex, the cost of infrastructure changed as you change processes. So that's kind of where we are. Where we see this technology going is that you actually design a product, you actually move into production, you have data. That data plus these models becomes your digital twin, and you can start to play tunes, you can start to optimize your process, not just looking at cost, but starting to looking at other KPIs, your sustainability KPIs, how and where you source your energy, your carbon footprint, where you source your materials, etc. And particularly an interesting thing for industry is, you know, what happens if government do certain things? How can we, you know, continue to be efficient in terms of producing parts in certain parts of the world and certain plants? So, you know, those trades are real trades that will need to be done. So that's the first example, which I hopefully brings you down to an idea of the kind of technologies that sit in this domain of digital manufacturing. The second one is slightly older. It's a project we did with an airframer a number of years ago, where we did the same sort of thing. We were building tools to understand their cost. But we identified that we could do, you know, LCA type calculations, and we worked with some of my colleagues in the school, Beatrice Smith, to basically to use the data from a cost model to do an LCA. You know, a description there of the processes, not necessarily for the audience, but for me to remind me what's in it. So we define the scope, we do our inventory analysis, we do our impact, we look at different scenarios, and we interpret what we can do. So in this case, we were working on real production processes, but we were allowed to generate a generic product. So this is an aircraft wing. We're focused on the manufacture of the top cover, which is carbon fiber composite wing. You know, the scope was that wing, that component, and we modeled the complete supply chain. So we modeled the production processes to make the part in the OEM, the whole way through, I think it was 5 stages or tiers of the supply chain, down to the petrochemical processes that were used to create the pan material, which ultimately became the carbon fiber, and the processes that became the epoxies, which together made up this wing component. And through that, we were able to identify, you know, a total emission to make this part. We were able to identify where the majority of those emissions came from, in terms of whether it was, you know, making the raw materials or whether it was making the part out of the materials. We're able to identify.
Adrian, sorry, I have to say that we might to rush now. Thank you.
Okay. We were able to identify where the energy was used, and then we were able to play tunes. We were able to look at, if you produced the product in different parts of the world, in the UK, in Sweden, etc., what would that do to your footprint? We looked at transport, etc., and played those tunes. So we're able to use that data set to answer some interesting questions to do with sustainability. And then really the challenges, the bit I wanted to leave you with, although I couldn't do it in time, is that these tools exist, but they have challenges. They rely on nominal part forms, which is not appropriate for circular economy when we have parts coming in that have had a pre-life. You know, these are big systems, and how do you model the big systems? How do you model them in real time to take account of real data? So lots of opportunities, lots of potential to do an interesting work, but work to be done. So thank you.
Thank you very much, Adrian, for a very interesting presentation. I'm aware of the time. If anyone has any questions for Adrian, please just put it in the chat, and then Adrian can address it by the side. So I think you have to move on with the presentations. Thank you very much, Adrian, again, for the very interesting presentation. The next speaker now is Kenny Maddock from the HSSMI. He's going to talk about simulating the sustainable future. And let me introduce Kenny to everyone. And Kenny has a bachelor's degree in aeromechanical engineering from the University of Strathclyde. And he's also got a postgraduate certificate in leading management transformation from Lancaster University. He has secured government funding for a large manufacturer in Scotland to support a large-scale capital and R&D investment project. He was project manager for the creation of the UK Automotive Council's new digitalisation roadmap, funded by BASE. And Hayes has written and submitted over 50 commercial bids as commercial manager for the HSSMI in Scotland, including several large grant bids for the OEMs and large manufacturing corporations. Kenny has over 10 years of experience in the manufacturing sector, including aerospace, defense, shipbuilding, automotive, and research and development. So thank you very much, Kenny, for making time to speak to us today, and I'll pass it over to you.
Thank you very much, sir. Just to confirm, can everybody hear me and see my slides okay?
Yes, we can see and hear you clearly. Yeah,
okay, thank you. Thanks very much for the introduction, folks. So, yep, I'm Kenny Maddock. I'm the Digital Manufacturing Manager at HSSMI, based just outside of Glasgow. I'm going to give you a quick overview of the company. We're a sustainable manufacturing consultancy. We work across multiple sectors, including automotive, batteries, hydrogen fuel cells, circular economy, manufacturing strategy, and digital manufacturing tools. And we work in those fields through funded research and development projects and also commercial consultancy. Our vision for the company and for what we want to support people to do is transforming manufacturing to drive us towards the net zero targets that the government have put in place and beyond that as well. And also our mission is to provide expert advice to help manufacturers to scale up, improve productivity, transition to a circular economy and circular economy practices, and accelerate manufacturing competitiveness, but also decelerate the negative impacts that manufacturing has on the environment, and again, drive towards the target of net zero. Today, I'm going to share two of the projects that we've used simulation on recently around the theme of sustainability. So the first one is modelling the scale up of some processes that we've developed in a project called Regale. Now, I wasn't responsible for the modelling. One of my engineers, Jack Bowen, who's on the call, was responsible for this. So hopefully, if you've got questions, we'll be able to answer them between us at some point. But to give you a quick overview of Regale, Regale stands for the recovery of gallium from ionic liquids. And I think some of the stuff that we've heard previously from some of the speakers about rare earth elements and rare earth metals and supply chains of those being a challenge, this is fairly pertinent to that. So it's looking at taking LED chips which have gallium in them, stripping them back to their component parts. So doing the comminution and material dissolution from there, then using the components that have gallium in them, using a special acid solution to put the chip in, to put the LED chip into it. And then overnight with applied heat, you end up being able to extract the gallium from the process. So you can see that there from the production. You have the LED, you see the acrylic lens, the chips, the driver, the aluminium body, and the base. And you split that into its constituent components and then break it down again, put it into the acid, add it to the acid and to the LED chip from there, and dissolve it in the solution. And you can see the results. You have this which is stripped away and it provides that gallium back as well. And that's a consortium project with S2S, Vaca Research, ECW, Recycling Light, IMF, and ourselves on that project. So the purpose of the simulation that we had here, it was a very simple process that had been set up as part of the trials. It was to demonstrate that it was possible to do that. So we used the simulation model to integrate the process, but also provide the people, the other partners, with a model that tells them what scale up is going to look like. So it follows on quite nicely from the previous presentation as well. It starts to give them insights into what sort of yields can be achieved based on the amount of information or the amount of components that you're putting into the simulation model. And again, to also assist with decision making around the types of technologies and processes and systems that that potential companies would want to put in place if they want to go for a process like this and scale it up. Looking at bottlenecks, line balancing, and highlighting any issues that you might have with production. We also designed a high degree of flexibility into that. I'll show you how the process is run in the background, but the idea was that you can start to really adjust the parameters very easily to demonstrate what sort of levels you get to with certain inputs of LEDs, or certain speeds or cycle times, or the number of machines, or how quickly you want to run the process, and what sort of shift patterns you'd maybe want to run in the facility as well. And what you can then do is use existing data once you have the facility up and running to fine tune it again and create your digital twin and take that forward to make sure that you're constantly improving your processes. So I'll just click play, and you can see on the right hand side here, this is using a software called AnyLogic. This is a simulation of a couple of the production lines that were designed using the processes. And you can also see here that it gives you the total gallium, indium, gold, and silver yield as well, based on the time that you manufacture. So you can see the values in US dollars, and you can see that it continues to creep up based on the components that are processed and then taken out of the facility and sent back to suppliers to create more LEDs from there. It's a collection and sorting of WEEE, disassembly, dissolving the chips in the acid, or the ionic liquid, sorry, to isolate the valuable material, and then electroplating of the gallium before it receives further treatment. And using the research and trial data from the project, the simulation gradually converts those lamps as they move through the process, demonstrating those potential yields, which you can see on the graph on the right-hand side there. The flexibility of the system I've already mentioned, but the entire thing's run through spreadsheets. So it plugs in, or the spreadsheet plugs into the simulation software. But what you're able to do is play tunes on the different aspects of the simulation model that you're running. So you can do, for example, LED lamps per day or delivery, and change that based on the month. So pallets per day, weight per pallet, the parameters in terms of the dissolution rate and the conversion rate, different parameters in the temperature rules, the choice of the liquid, and so on as well. So you can start to use different liquids and different types of system to dissolve the gallium and to bring that back into the supply chain. Now the numbers there are demonstrative only; they're not part of the actual project because they're currently confidential. But it's using current market prices for gallium as well. But you're able to change that, and you can predict if gallium is going to get more expensive or cheaper based on any more discoveries we have of it, or other aspects that you'd want to play with on those models as well. Sorry, I just need to go and hang up the phone. Apologies, folks. The second project that I'm going to share with you this morning is one which is a slightly different type of project. So this is a research project, but we had a physical application at the end of this. This was a project that we ran in Scotland called HyDyne, and it was simulating hydrogen injection on the ferries that are used in the Orkney Isles. Give you an overview of HyDyne. It's hydrogen diesel injection in a marine environment. And currently in the Orkney mainland and the Shappin Sea Islands, and also on E-Day, they have a system called surf and turf. Surf and turf is wind turbines and also tidal turbines, which are used to produce energy for the islands. And any curtailed energy that you get from those, when the islands either don't need it or the national grid doesn't need it, then powers electrolyzers across the chain of islands to create hydrogen. What we then looked at doing with a shipbuilder called Ferguson's, who are on the Clyde, and a couple of other partners as well, was looking at how we could displace diesel in one of the engines and demonstrate the efficiency increases that you can get as a result of using hydrogen to displace the diesel in the systems. Now, this was done on one of the auxiliary engines because of the requirements to store hydrogen that you need to meet, because obviously it's a fairly volatile gas, and there was we had to get approval through Lloyd's Register as well to make sure that we could control and keep the hydrogen safe on the ships as well. What we did with the simulation model, after we proved the concept and proved that it would work, we built a simulation model of how the ferries operate in the islands, but also how the hydrogen would be transported around the islands as well, because it doesn't always mean there's not always hydrogen in the correct place to refuel the ferries. So we had to model things like a hydrogen trailer carrying 250 kilos of hydrogen on the ferry going to another island. You need to understand the carbon footprint of that and the impact that having to transport that hydrogen has on the displaced carbon. Looking at tractors carrying trailers and things like that, modeling that too. Looking at the Shappin Sea vessel when it arrives and how it's going to be refueled with the hydrogen, and looking at the capacities, looking at the deposit from the ferry, and modeling all of those as well. So you can kind of see on the right there, you've got the trucks that are queued, the electrolyzer, the storage, and then also the source of the different hydrogen, how things move, where it moves to, and so on. So we built a logic map for the ferries traveling at their usual times, and using any logic, superimposed that over a map to demonstrate the ferries moving between each of the ports. So just click play here. You can see that this is kind of starting during the day, and then it progresses through. So you can see the ferries moving from Kirkwall up to E-Day here. And then at the right-hand side, you can see too the hydrogen that you've got at FC, and then the ferry hydrogen as well, but also the total amount of hydrogen that's being produced and the hydrogen that's currently at E-Day. So you can see there there's a big drop off because that hydrogen has been used to fuel to refill the ferry so that it keeps its sustainable nature and taking it from there. You can then start to change the truck, where the source comes from, and again, try and understand what the impact of that is going to be on the carbon footprint and so on. So we ran two scenarios. So there was one where there was 20% and 60% diesel displacement on the ferries with the following results. So kind of 20% showed that the total CO2 displaced was around 22,000 tonnes. And produced was 11,500 tonnes, so a net displacement of about 10,000 tonnes of CO2. And then at 60%, obviously it's a lot higher, displaced 62,000 and produced 25,500, and then displaced 37,000 as well. So you can see that the CO2 impact is the hydrogen transport itself. So we also were able to start to think about how we can influence the transportation of the hydrogen to reduce the impact that that has overall on the ability to do the displacement on the engines and the displacement on the diesel propulsion systems as well. I'm going to stop there, folks. I'm conscious of time. If you do have any questions about the projects and the applications of them, please do let me know. I can try and answer them just now or get back to you once I've spoken to some of the team about it.
Sorry, Kenny, there is one question which you can quickly take.
Yep.
From Royujin. Is the Regale software developed by you shareable to others for running simulation?
Sorry, the software, so the actual simulation model? Or the software? The software package is any logic that's freely available to anybody. I'd need to go back and check what the rules of the consortium and the research project are in terms of the coding and how that model's been run. I can't answer that straight off the bat if that's what they're after.
Okay, and they can get in touch with you directly.
Yes, they can.
Yeah.
I believe I think there's also a webinar on Regale, I think next week, which I can share details to as well, and you could send that to folk if people want to come and see that in a bit more detail.
Yes, please. And if you can put it into the chat box, that would be great help.
Yep, I will do.
Okay, thank you. We can move to the next one now. Thank you.
So Pamela, waiting for Joe.
Yeah. Yes, I'm here.
Okay. Hi, Joe.
Hi, Allan.
Words about you, Joe. So Joe Armstrong has more than 25 years of experience within the surface metrology industry, and that includes contact and non-contact technologies for both form and texture. Joe started as a laser test engineer, moved into applications, then into sales and business development. Working in sales, Joe is now responsible for Polytech's international customers. So over to you, Joe.
Okay, so I'm just getting my presentation going. Okay. Okay, well, very interesting presentation so far. I've really enjoyed them. My presentation is a bit of a different flavour to some of the presentations. I'm going to be giving a quick insight to Polytech. Now, Polytech as a company is most famous for non-contact vibration measurements. We started making our first laser vibrometers back in 1987. And of course, we started to understand that there was a need not just to understand how something is behaving dynamically, but also in terms of its shape, its texture, and how it looks and feels. So we had a breakthrough of our surface metrology for topography measurements in 2004. And in 2017, we celebrated 50 years. So it's just a quick insight to Polytech. So what I'm going to be introducing you to today is our key surface topography measurement system using the coherent scanning interferometry, giving you an indication of some applications. Mostly I'm going to be focusing around optical solutions, so optical quality surfaces, but of course the bandwidth of the type of applications we can sort of assess is quite wide. I've measured everything from rocks to insect eyes. I mean, people try all sorts of sort of weird and wonderful stuff these days. So there's quite a bit of flexibility. You can see in the bottom there is a coin. It's a bit cliche, but it just shows the nature of the detail that we can recognize. So a quick introduction. Polytech has a family of products and they're maturing nicely. We have two key product types. Let me just see if I can adjust my mouse. So I've got a laser pointer. We have the macro lens systems and we have the microtape system. We have some entry-level products. Here we also have a multi-sensor configuration where it includes both macro lenses and confocal sensors, which is quite interesting. Now, all our different instruments use the same technology, which is a coherent scanning interferometry. It's a type of white light interferometer. It's a classic interferometric setup. We have a camera, we have a light source, we have some way of separating the light into two optical paths. So we have the test and the reference. And then we change the distance of a reference plane. By changing the distance of a reference plane, we can start to look for the best focus of a surface. And as we collect information coming back from the surface, we can then signal process this. And we can collect information and we have sensitivity to the sub-nanometer region. And we can get that over quite long measurement ranges as well. So why coherent scanning interferometry? Well, you can see your surface. So if you have scratches or defects, seeing your surface in an aerial format really allows you to see and understand. It takes that human eye sort of coordination where you can actually see something and do some pattern, something which robots are still challenged to do. The measurements are quite accurate and quantitative. You get good surface characterization, so you can measure textures, you can measure shapes, you can measure a variety of surface types. All measurements are non-destructive, so no need for surface preparation. Measurement times are extremely quick, especially when you consider the sensitivity that you have. And you can measure all sorts of different material types. It's worth noting for industrial applications, measurements are all high resolution, very repeatable and low noise. So for any manufacturing process, what you need is good sensitivity, good stability, and you need to be able to take those numbers, which you can then relate in a reliable and stable way to any manufacturing process. So this is really key to whether the technology is going to be successful at suiting the analysis and feedback mechanism for any manufacturing process. As I said, we have two flavors of instrument. We have the microscope and the macroscope. People always ask me, well, which type of instrument should I be looking at? My advice is always ask the question, how big, how small? So for the microscope type systems, you have optical sensitivity from 0.46 of a micron. Your digital point-to-point spacing is much higher sampling rates than that. But of course, you're going for a microscope lens. So these are good for making small things look big. Whereas the macroscope type systems, they're good at making larger things look big. So you can have a single field of view from 45 millimeters, and with image stitching, you can easily achieve over 200 millimeters. So a different flavor of instrument for different applications. There are some other differences, and these are really enablers to how well you can measure a surface. So it's like the strategic approach. If we consider a microscope type system, then you have a higher magnification, you have a higher XY sampling rate. But as you can see, your lens is typically much closer to an object. You have to turn the light much faster. So if you start to look at recessed surfaces, you start to get maybe a bit of shadowing. Whereas differences with the telecentric lens, you have a larger field of view. The consequence of that is a lower XY sampling rate, but you get very good penetration into a surface. So you have a different XYZ capability. For both instrument types, you then have to look at the numerical aperture, you have to look at the slope handling ability of your lens system, but you can go beyond mirrored surfaces, providing you get some localized scattering on a surface. You can achieve quite good slope handling ability. With a macro lens, you can measure maybe 65 degrees. With the microscope, I've even measured surfaces up to 80 degrees. So the performance, if a surface is compliant, can be surprisingly good. And that's pretty much the same for all optical systems. The nice thing about the macro lens, large field of view, don't really need to do so much stitching. So the quality of the data over larger areas, if you're looking at flatness type applications, so if you're working with fuel injectors or pumps or sealing surfaces, and you're really looking at the efficiency of these mechanisms, then it's quite a good idea to look at the macroscope type systems. Now with our products, it's nice to say different instrument formats suit different applications. So if you are looking at wafer bow, the ProSurf naturally has a larger measurement area and will suit the flatness measurement of a wafer bow. It will suit the inter-surface relationship of maybe a microstructure. It can do larger area counting. So if you want to look at solder bumps, you can do that as well. Whereas when you want to look at maybe more fine details, such as maybe on a MEMS device, maybe a surface texture or a small etch surface, then you'd look at the microscope type system. Interestingly, when you're looking at wear mechanisms of surfaces, sometimes you can find that you're caught between the macro and the micro world, and it's almost good to consider a crossover measurement capability. So it's worth considering that. So we have two flavors of the microscope type system. We have our standard compact system, which we call the micro view. Internally, we refer to it as the TMS 1400. This has the continuous scanning technology. What we mean by this is if you're scanning 1 millimeter, you can get your sub-nanometer sampling rates in Z over that 1 millimeter. If you are using the upgraded MicroView Plus, as we call it, again, you have the 100 millimeter closed loop scanning where you can get the high Z sampling over the large ranges, but you have two additional items. First, you've got the closed loop feedback. So your XYZ coordinate system has a reduced measurement uncertainty, but we also have available within the system the option for color information, which can be very useful for looking at wear mechanisms, looking at tribology features, maybe looking at different material types and giving you an indication of where one material starts and the other ends. Of course, here I'm talking about optical polishing, giving some examples of different sort of fine measurement surfaces. So I have a polished silver mirror surface. You can see the average roughness is 0.29 nanometers. If you apply some filtering, so you want to conform with a standard such as ISO 10110, then you can see you can get down to 0.065 nanometers, which is pretty incredible. And at the same time, you can look at scratch and dig errors as well. Give you an idea of Z resolution. Here you've got a high magnification measurement of a scratch on an optical quality surface. You can see it's in the order of 0.5 nanometer, and the XY size, the diameter of this is in the order of 600 nanometers, but you can easily see what you can see from the valley to the peak of a surface. Small defects, scratches, you can get really good details. That makes us particularly suitable for applications like single point diamond turning, where you take a diamond-like tooltip, which is in the order of 1 or 2 microns in radius. You can then precision turn, control the texture and the shape of these surfaces. Here you can easily get down to a couple of nanometers in terms of texture, but they're quite demanding in terms of the types of shapes that you might want to produce. Like I said, for surfaces that are compliant, even on surfaces that have some quite good surface finishes. Here I have an example of a surface that has a 100 nanometer RA surface texture, and we're still able to measure maybe a slope of 75 degrees, providing that surface is offering the instrument some sort of micro nano scattering effect on the surface.
Joe, sorry, can I please say we might need to wrap up soon?
Okay, I'll go quick. So surface texture measurements, and of course, once you've got data, you can measure steps, you can measure shape, you can measure discrete features within the shape, you can measure areas. It's always nice to talk about strategies for measuring different steps and shapes and angles, how you're going to interrelate to these surfaces. You need to take a little bit of care there. If anyone has any questions on strategic approach to measurements, please contact me. I'm quite happy to discuss. You can do form removal measurements. This is of a diffractive optic. Ideally, you'd want to see this as a balanced process, but here you can see there's a machining error on this surface, and there was like a spindle wobble we picked up, and you can actually see this rippling across the surface and this unevenness on the profile here from the spindle wobble. So the applications that microscope suits is surface coatings, texture, micro parts, machine parts, various material sciences and micro devices. Just a quick, because I'm running out of time, a quick introduction on the macro lens system. This has a floating magnetic drive. So the capability of measuring large steps is just incredible. If you measured a 50mm step, your measurement uncertainty would be good to 1 or 2 microns. It is really an excellent product for large step height measurements. Pretty unique. And with the macro lenses, you can measure the flatness. It's specifically designed for flatness. You can get some cone angle measurements. And here I have a measurement where I'm measuring down a hole, which is almost 50mm, and we can measure that. Really different behavior to that of a microscope type system. And I think this image here really sums up that capability quite well. It's very good for intersurface relationships. So looking at the relationship of islands to optical polished surfaces, you can really measure like flatness down to the 100 nanometer level and get intersurface relationships. Here you can look at the manufacturing process, relate to the manufacturing of optics, which is a popular application, and get real-time feedback on the performance of a manufacturing process and identify when you've got problem optics, problem surfaces. So some repeatability, you can see there's a millimeter step and you're repeating to the micron. The performance is excellent. Large area defects, and hey presto, I can wrap up. And of course, this talk was just to give you a quick impression of what Polytech can do, invite everybody to make contact. Maybe you've not associated us with this particular industry sector, and we welcome all input, and we're happy to develop any working collaborations with anyone that's out there who would like to have support or advice regarding the measurement of surfaces and surface types. Thank you for listening. I hope everybody enjoyed my quick and brief introduction to Polytech.
There is a question for you, Joe, from Marin. Can your technology be used for obstacle detection in a real environment?
Sorry, can you repeat that?
Can your technology be used for obstacle detection in a real environment?
You can measure a surface, but you have to remember the surface has to be still when measuring. This is always a problem with sort of static-based measurement technologies. So providing you bring the part in and it's got a feature or a shape and you can quantify that as a difference, then you'll get a result that's usable. If someone wants to measure something wobbling around like a motor, then look at a laser vibrometer. They're specifically designed for measuring surfaces that are mechanically shaking around and moving, looking at harmonics, looking at frequency changes. I mean, with that type of technology, you can even measure a bridge. I once measured the Humber Bridge with that measurement technology. So it's always looking at the problem and seeing what you can measure, how you can measure it, and trying to understand how a technology would relate to being useful for that particular approach. Any more questions, or are we happy?
I think it's done.
Good.
There are two new messages. Yeah. Well, Nestor asks, Joe, if you can share your email address and contact, because he might like to get in touch with you.
Yeah, okay. Email is j.armstrong@polytech.com.
I'm going to put it in the, I'll put it into the chat box.
Okay, perfect. Everybody's welcome. I try to do my best, and I've seen some really interesting applications already where I think we have some suitability. Polytech has done its best to keep the topography a secret, but when people discover us, we're quite popular, and we're trying to grow this business sector for us. So all inquiries welcome.
Okay, thanks very much, Joe. Quite a few people have asked how they can access they've asked, is the recording available? And the answer is definitely yes. Pamela, do you want to explain how the recording can be accessed?
Yes, I will put it on our YouTube channel, and I will send a link to everybody who registered and the people who have already part of our networks.
Yeah, you have to sign up to the network to access it, which is free, no charge at all, but we do require you to register. Okay, I think we've kept remarkably to time. Luciano, do you have any final comments at all?
No, just to thank all the presenters for the brilliant presentations and perspectives, very interesting perspectives they presented today. Thank you very much for all the speakers, and also for Pamela and Cinziana for organizing this event today. Thank you, Allan.
Yeah, thanks very much. As we said, this is our first joint event, and really it provided a taster for some of the things we're doing, and I think we'd like to expand on some of these. If anybody's got any thoughts or comments about particular aspects that we should expand on in any future webinars, we're very much, both Network Pluses are very much into working with other people, with other academics and with other industrialists. So, like I said, this is the start of joint activities.
Yes, indeed. Thank you. And if you would like to get in touch with us, please don't hesitate to contact us. And I'm going to type down my email in the chat box, and you can access it us from our website as well.
So any
Thank you.
comments, gratefully received. Send them to Pamela. She's volunteering. And, so either to Manchester or to Aston, that will greatly receive any comments, critical or otherwise, about the webinar. Thank you very much.
And any feedbacks to improve what we can do better next time, please let us know. Thank you.
Thank you.
Thank you.
All right.
Goodbye, everyone.
Goodbye, everybody. Goodbye.
Bye. Thank you.